All right, guys. Today, we're going to be discussing what we talked about at the end of class last time, which is rewriting trig functions. In general, before I begin, I want to make sure to emphasize a very, very important point. Everything in this section, you can apply algebraic rules to. That is why you can notice on the side wall, there are a couple suggestions for step 2 that are all algebraic in nature. We have factoring, which is algebraic, distributing algebraic, squaring, which is algebraic, combining fractions, which is algebraic, and of course the opposite of each of those. You can factor, you can distribute, if you can square root. If you combine fractions, you can also take them apart. The reason I say that is because for some of the ones we're going to talk about today, we have to make significant modifications to the formulas we have on that cheat sheet. Let's start there. In class last week, when we talked about these formulas for the first time, we made some modifications to rewrite them to begin with. This section has so far been the hardest one, so I suggest those of you that aren't paying attention to do so. First, the Pythagorean identity, sine squared plus cosine squared equals 1. Last week we talked about one of the ways to modify this was by making a simple algebraic adjustment. We added or subtracted to both sides to make this look different. Examples we had from last week were, we subtracted sine to create cosine squared of x equals 1 minus sine squared. This was considered an alternative. We also could subtract the cosine and do the exact same thing. So this becomes sine squared equals 1 minus cosine squared. These were two that we talked about, but these are not the only two. Do not mistake that statement. You can do anything that you could do to any other algebraic equation, meaning you can add to both sides, subtract to both sides. We can multiply both sides by a constant. We can divide both sides by a non-zero constant. You may square both sides. You may square root both sides. Anything you can do to a standard equation, you may do to these Pythagorean identities and use it to try to solve a problem. Which is why, let's talk about our very first problem today. This one states, I want to take a trig function, which is written in a specific way, and rewrite it as a new function with only a new single trig function in it. In this case, let's talk tangent. I want to rewrite tangent of x in terms of secant of x. Oops, come on. Secant of x. So my long-term goal, somehow convert just tangent into something that has secants in it. Now, a word of warning, it will have constants in it too. It will have other operations in it too. What it means is I don't want to have tangent anymore. I don't want sine. I don't want cosine. I don't want cosecant. I don't want cotangent. I want a new version of this formula containing only secants. So, how do we do that? Well, first, I want you to recognize that there is a distinct relationship between these two. Not the way they are written right now, but there is a relationship. We've actually already defined it on our cheat sheet. Go to, I believe, the second Pythagorean identity, which states the following. Tangent squared of x plus 1 equals secant squared. Verify that for me. So this connects tangent squared with secant squared.
Is that the problem?
We'll figure it out. The door's open.
Is that the problem?
This is the Pythagorean identity. But my problem is, I want to get tangent to just secant.
Is that what I'm starting with to get?
Yes. Okay. I need to find some way to modify this current function, which is in terms of tangent squared. So it becomes in terms of just tangent by itself. Now remember, this trig identity, I can do anything to this trig identity that I can do. Yes, sir?
Do you have a can of air, like a black bear? That we borrow.
Let me just back there. Ah, right back there. Black shelf? Right, is it? Next to the weird wooden contraption that looks like he's going to poke your eye out.
I know we're looking for like the dust can. You don't have it.
Right next to it.
That's what's
It's back in the black. Oh, I see it.
Check to make sure there's some in it.
Yep.
There you go. Okay, one more time. I am here. Connecting tangent squared to secant squared. I want to get tangent by itself. I have every algebraic tool to do so.
Subtract 1.
Subtract 1 would get tangent squared by itself, but then I could do another step 2. So subtract 1 from both sides. This would give me tangent squared equals secant squared minus 1. That's closer.
Did you do a square root?
If I do a square root, which I'm allowed to do to any function, I do it to both sides.
Do you have to drop the x?
Oops, thank you for correcting me. I should not have dropped the x. Oop. Thank you. Okay, let's talk about what happens to this problem now. Because this will get tangent by itself. Remember, squares and square roots naturally cancel, meaning tangent is now alone. Tangent of x. On the right-hand side, we end up with something a little bit nasty. But what I want to point out about that nasty equation,
There's a square root on that side.
secant squared of x minus 1. Notice that this answer is in terms of just secant. Yes, it is secant squared, but it's still just secant. There are no sines. There are no cosines. There are no tangents. There are no cosecants. There are no cotangents. It is just in terms of secant. Which means for this problem, we've actually successfully found a relationship between these two, relating tangent by itself to secant. No. So first, the solution. The relationship between tangent and secant is as follows. Tangent of x is equal to the square root of secant squared minus 1. When we get back, I will explain why we can't cancel any farther. Okay? That is our solution. Connecting tangent to secant.
Is it because square root of 1 would be an irrational number?
No. It's property from algebra.
Yeah, I actually did. That's the first thing I did.
You too, guys. Okay, Giselle. Giselle, you asked specifically why this isn't simplified any further. As a reminder from algebra, and this is just a fact of algebra, which I can show with a very simple example, but as a reminder, the square root of two things being added or subtracted, it does not matter which one, never, ever simplifies into separate radicals. It just never happens. I can show this with a real simple example that should be easy to do without a calculator. So let me show a very simple one, okay? What if I had the square root of 9 plus 16? Well, what you're saying is I can split that apart, because normally we wouldn't do it for this one, but let's pretend we use the same logic you just did, that I could split it apart. Well, this would become the square root of 9 plus the square root of 16. Well, the square root of 9, that's 3. The square root of 16 is 4, so we get 3 plus 4, which is 7. But on the left-hand side, 9 plus 16 is 25, and the square root of 25 is 5. That's why this doesn't ever work. You can never split it as long as there is addition or subtraction. You cannot do that. If it was multiplication or division, I would be right on board with you. Right? Yes, let's do it. But because of that subtraction sign, this is as far as we can go. Okay? By the way, that is one of the most common mistakes people make in this section. So thank you, Giselle, for bringing it up. You will not be the only one that will make that mistake, and people who aren't paying attention are going to make it. I won't be sad. So this is as far as this function goes. So as a reminder where we started the problem, we started with tangent. We found a path to get to secant using one of our trig identities. With that path, we had to modify one of the trig identities, but we can do that as long as we follow appropriate algebraic rules. Let's do another example. This one is again out of text. This is number 26. So it's an even. So it's very similar to one that you had that's an odd. 26. So on the previous one, we found a direct connection between the two pieces and used that to solve. This one is not quite as nice, but it's real close. Let's take a look. We have here number 26. It states secant of x is the function we are starting with. We want to write it in terms of sine. Now, there are a few ways to do this. For this section, there are in fact a number of different ways for each one of the problems that we have in this section to rewrite them in a different way. If you simplify them down, they eventually all end up being the same answer. But there are a lot of different ways to do so. So, in this problem, as you might notice if you're looking at your cheat sheet, there is not a direct path connecting these two. There is nothing that connects secant to sine. It just does not exist. So I have to get creative with these kind of problems. Say it again, Devin.
I'm thinking to myself right now.
Thinking to yourself is helpful right now. Come on. Take a look.
I was thinking,
I have no way, if you look at your cheat sheet, there is nothing that connects secant to sine. There's no Pythagorean identities. There's no reciprocal identities. There is nothing that connects secant to sine. But I bet there's a path where I am creative with how I get there. So that would get me in terms of tangent, Brian. But does tangent get me closer to sine? So Brian recommended a common path, which is to try to convert secant into tangent, which is a path you can take. The problem is, always consider part 3. You know you want to get closer to sines. If I convert it to tangent, unless there's an easy way to get to tangent, that doesn't help me very much. I'm not saying it's the wrong path, but it will take you almost 3 times longer than the right path. Now, if you're smart, you might try it, but it will take a long time. Okay, come on, guys.
can you put a secant in cosine?
That's how we're going to do it. What I do is, I start by taking secant and turning it into cosine. Why would I convert it into cosine?
Because step 4 is if all else fails, convert it beside the
Very good. And I'll bet there is a connection between these two. Something that connects sine and cosine together. In fact, it's on the board. It's our first trig identity. So we use the fact that we convert secant into sine and cosines to get this to become a cosine function. Once it's in a cosine function, we then have a simple way to convert it using this version of the formula to convert it into secants into sines. Let's do it. To start with, Devin, you were exactly right. Step 1. We take secant of x and turn it into 1 over cosine of x. That is a reciprocal identity. So, this is using an intermediary identity. I don't have a direct connection between secant and sine, but I do have a connection between secant and cosine, and a connection between cosine and sine. Notice how one uses a reciprocal identity, the other piece is going to use a Pythagorean identity. So it uses 2 different ones. This is very common. If you do not have a problem that directly connects them, see if there is a secondary path using reciprocals and other versions of it. Okay, now once again, I am left with a problem that does not connect the 2 pieces I want. I have cosine in my problem. I don't want cosine, I want sine. How do I get from cosine to sine? Big hint, it's the same way we did it on the last problem. So we use this function. The function states we have sine squared plus cosine squared. That connects sine and cosine together. Now, it does not connect single sine and single cosine. It connects sine squared and cosine squared. So we're going to have to make some modifications to it. But it does connect them together. So let's start there. We start with sine squared plus cosine squared. This is what I'm given. Now keep in mind, I want to get rid of the cosine and replace it with the sine function. So the best way to do this is to solve for cosine. I've already done that on part 1, so I'm going to do that step. I subtract sine from both sides. And get this formula. Cosine of x squared is equal to 1 minus sine squared. This connects cosine to sine, but it connects cosine squared into a sine function. I don't want cosine squared. I want to get rid of just cosine by itself. So how do I get it back to just cosine? Square root it. I square root both sides, same as I did in the previous one. This allows me to get my function to be in terms of a single trig function cosine. So on the left hand side, I get cosine of x. On the right hand side, the square root of 1 minus sine squared of x.
Which one is the middle column? Like, which one are we trying to work out?
We're trying to get from secant to sine.
So we're doing this?
I'm using this to help me.
It's confusing.
So what I'm doing is, I cannot use the formula given on the page. The formula on the page is sine squared plus cosine squared equals 1. That's all on the cheat sheet, right? That does not help me in this problem because the problem doesn't have either one of those things. It has secant. So what I do is, I convert secant into cosine using a reciprocal. That's one of the ones on our cheat sheet. And the cosine, I'm now modifying this formula to get cosine by itself, allowing me to take this function and change it. What I end up with is as follows. 1 over square root 1 minus sine squared of x. This function is now a function that used to be in terms of secant and is now in terms of just sine.
Don't you not allowed to like have the square root on top?
Good point. In algebra class, I demand that you continue going. This class, I will tell you this is an okay answer. I'm not worried about whether or not you can algebraically simplify. I'm worried that you can get the trig function by itself. That's what I'm more worried about. So this is actually a fine solution. One more time, because this is a very confusing process if you're not looking for it. One more time. I started the problem knowing I want to connect secant to sine. With those two pieces, I have to first find a way to connect them together, so I use cosine to do so. So I take secant, turn it into cosine, but I can have a way to connect cosine to sine if I modify the formula. So I start with the formula I'm given, I apply algebra to the formula to get cosine by itself, and I plug it in. Again, this gives me a single function in terms of one variable, sine. I found it by using a reciprocal identity and rewriting a Pythagorean identity into a new form. We talked last week about how you can do this, and it happens pretty often, but we talked mainly last week about doing it by adding and subtracting. Well, here we can do it by squaring and square rooting just as easily. Remember my long-term goal, to convert secants into sines. I convert secant into cosine, then cosine into sine. So, my solution, number 26. See you, Doug. See you. Now, we'll do another example here. The same process goes through the entire time. We have to figure out a pathway that connects identities we know with what we currently have. Next one.
Can I ask you a different question?
Sure.
Okay, so on number 7 on the homework, it has like the answers in secant.
Yes?
But I simplified it all the way down to sine squared of x, and like it would be even more complicated to put it in secant. Like it makes more sense to just stop here. It'll.
What?
What are those? Those two. That came from there. No, that came from there. That sine x still came from there.
What's in there?
Oh, that's plus. But those two.
Okay. Next one. Number 28. Cotangents into cosine. I can't stress this enough in this chapter. In general, the hardest thing about this chapter is that there is a bunch of algebra mixed into the trig. You have a trig formula, you then have to algebraically manipulate it into something you can actually use. That is difficult. If you're not good at the algebra part, you cannot possibly then do the trig part. So, On these kinds of problems, you'll notice that I constantly am using algebraic properties to try to rewrite them. That is because of what I'm trying to do in terms of my steps. I'm looking to factor, distribute, square, combine fractions, all that stuff. I'm paying attention to what my solution looks like and converting the signs and cosines as necessary. But that third one's really big. Noticing my solution. If I want to get this in terms of cosecant, I need to look for something that connects the two together in any way I can. If there's a direct connection, great. If there is not a direct connection, I need to find a way to connect them together. Some of these will be very easy, one-step problems. Others will require a lot of algebra manipulation to get them there. This is one. On the list, it's kind of in the middle. Take a look. I want to find a conversion that takes cotangent and writes it as something involving cosecant. So again, look at our cheat sheet. On that cheat sheet, there's probably a function that uses cotangent and cosecant. And if there's not, there is one that gets me somewhere in between them. So look at that cheat sheet. We have one that connects them automatically?
Yep.
Yeah, we do. We have a function that says cotangent squared plus 1 equals cosecant squared. Now again, my goal is to get cotangent by itself written as something involving cosecant. This is close. It has cotangent squared plus 1. I want to get to cotangent.
Subtract 1, take the square root.
So what do? I apply algebra. Okay, my goal is I want to get from here to there. Right now I have cotangent squared plus 1. So I apply algebra to get rid of those pieces. I subtract 1 first. Again, algebraically, I always move the numbers first. This gives me cotangent squared of x equals cosecant squared of x minus 1. We did that stuff last week. But now we're taking it a step farther. Any algebraic step we can do in algebra 1, algebra 2, we can do with these functions as well. If I want to get to, again, just cotangent, I can modify this equation. I square root both sides. That'll give me just cotangent. I square root. On the left-hand side, I get cotangent of x. Notice I want to start with just cotangent of x. And what does it equal? The square root of cosecant of 6 minus 1. Notice I have a function that relates just cotangent to something involving cosecant. This is my solution.
That is equal to.
All right. Last one. Let's do the homework one. 33. That's not an intersection. This is verified. Let's do 19. Number 19. 19 is a homework problem. And on 17, we're going to talk about the trick that 17 requires. 17 and 23 both require the same trick. Once you see it, you'll remember it from algebra quite a bit better because it's an algebraic trick. Remember, I said it and I'll say it multiple times. The algebra is what's going to mess you up. You have to have an algebra trick to solve 17 and to solve 23. Okay, let's do 19. We have the function 1 over sine times cosine minus cotangent. My goal? To get everything in terms of cotangent. You'll notice that part of this is already done. The right-hand piece, it's already in terms of cotangent. I'm probably not going to mess with it. Which means I'm really going to focus upon what's happening with this left-hand piece. How can I rewrite this left-hand piece to be something involving cotangent? Okay. This is a version of a difficult problem. because you notice there's more than one trig function you have to work with at a time. So in the previous ones, it was more straightforward because there's only one trig function, you just have to find a single connection between the two. These ones take a little bit more work, but the same ideas will happen. I have to find some way to get 1 over sine times cosine to become something involving cotangent only. No more sines, no more cosines. Let's talk about how. First, I'm going to start this problem by using one of my identities, the reciprocal identities. I have reciprocal identities that deal with sine on the bottom and cosine on the bottom. Look at your cheat sheet, please. How can I rewrite 1 over sine times cosine? And you'll notice as I say that again, I'm ignoring the right-hand piece because the right-hand piece is fine. I'm looking at my solution. I want it to be in cotangent. It's already there. Ignore it. The rest before we need to fix. How can I rewrite 1 over sine times cosine? Close. And I think you may have just missaid it. This should be cosecant times secant. What are those two, Brian?
1 over sine would equal to.
So the 1 over sine, this version is cosecant, and this version is secant. Can't have been much. Okay, well that's a little better because I have something that relates cotangent to one of those two pieces. The other one, not so much. But at least I can get one of them to work right now. If you look at your cheat sheet, I believe there is a connection between cotangent, which is what I'm looking for, and cosecant. In fact, I think we had it on the board for a while. What is the connection between cotangent and cosecant?
Are we still in the reciprocal, Pythagorean, inverse?
Yes, still those four are the main options. But now we're just algebraically modifying some of those four. So in this case, look at your Pythagorean identities. You see one that relates the cotangent that we want with cosecant.
Ooh.
What do you see?
Cotangent squared x plus 1 equals cosecant squared x.
So I hope everybody can see that this, with some work, will connect the cotangent and the cosecant in this problem. I don't want cosecant. I want cotangent. So if I can use this, I can modify this sum and hopefully get them. That will take care of the cosecant, but it does not solve the secant. Okay, so let me take this one piece at a time. Let's first go over here. I want to get rid of cosecant. I have cosecant squared. Let's square root it. This will solve me for cosecant. So this becomes, on the left-hand side, we get a nasty radical. On the right-hand side, just a nice cosecant. So, as a reminder from algebra, this is again referred to as substitution. Anywhere I now see a cosecant, I can replace with the square root of cotangent squared of x plus 1. You may think that looks worse. Long-term goals, guys. Long-term goal, get it in terms of cotangent. That's in terms of cotangent. Golden. Remember, I told you you don't have to simplify these as long as you get them in terms of cotangent. So what do I do over here? Now, instead of cosecant, I replace all of cosecant with the square root of cotangent squared plus 1. I have not fixed the secant, so I'm going to leave that there. I have not done anything to the cotangent because it's already good to go. So 2 out of the 3 pieces are now in terms of cotangent. I'm looking real smooth. Only one problem. I got the secant floating around. It's an issue. I don't want secant. I want everything with cotangents. And if I look at that cheat sheet, as Haley did just a moment ago, there is no connection between secant and cotangent. One more time. If I look at that cheat sheet, under the Pythagorean identities, there is no connection between secant and cotangent. And even if you look at the other identities, the reciprocals, the quotients, there is still no connection between secant and cotangent. So I have to be creative. Say again?
Switch back to cosine. Does cosine have a relationship?
Good question. Let's look at our list. Does cosine have a relationship to cotangent? Cosine, cotangent. They have a connection. We good?
Is it cosine?
Cosine and cotangent?
No.
It does not. Secant and tangent have a connection. Why is that helpful, Daisy? So there's the two pieces. I cannot connect secant to cotangent directly. So you said to connect secant to tangent, and tangent connects to cotangent on the reciprocal rules. That's exactly what I'm going to do. Ready? You walk me through that first piece? How can I rewrite the tangent rule, which is tangent squared of x plus 1 equals secant of squared of x? Square root both sides, just like we did with the previous one. This will give me something a little bit nastier, but that's okay. It's getting me closer to my long-term goal. Remember, step 3, pay attention to your solution. I want cotangent. This gets me closer to cotangent. This becomes secant of x, and then this nasty square root. Tangent squared of x plus 1. So I'm going to go over here. I replace my secant. So I still have this piece. This piece is solid. It's good to go. I have this piece. It's solid. It's good to go. It's this piece in the middle that's still a problem, but it's closer to what I want. So times the square root of tangent squared of x plus 1. It's still an issue, but it's closer. How do I know it's closer? Because there's a relationship between what I have now and what I want.
Cotangent is the reciprocal of tangent.
That's right. My solution. As a reminder, tangent is 1 over cotangent. It is a reciprocal rule. So everywhere I see a tangent, I can replace with 1 over cotangent because it's on a reciprocal page. My final solution. It looks nasty, but notice it does exactly what it's supposed to do. I took everything in this problem and rewrote it in terms of just cotangent. Here we go. The first piece, big square roots, cotangent squared of x plus 1. The second piece, times. Okay, instead of tangent, I write 1 over cotangent, as Devin said. So if it's tangent squared, it's 1 over cotangent squared plus 1. And then finally, minus cotangent. Everything has just cotangents in it. That is the solution. One more time. I started with two pieces that did nothing to do with cotangent. I converted them into a different form using reciprocal property. And then one of those pieces converted directly, right? Cosecant and cotangent are directly related. The other piece did not convert directly. I got to get something closer. So I used secant to get to tangent, because tangent is close to cotangent. This is the logic of these kinds of problems, the part that makes them fun. Because you have to figure out the logic that fits between the two. Sometimes there's a nice direct path that directly connects the two together. Think of the last problem. It was simple. We had a formula, we square root both sides, we were done. This one, more complex, because we had to take one piece that we did that to, the other piece we had to find a workaround. I did not have a connection between secant and cotangent, so I made one using tangent. This was a homework problem. We will continue working on these problems as we come into class tomorrow. These are not problems you want to sleep on. These problems are tough. If you call through and try them out in class and ask questions, you will do far better than if you just do your own thing and try them on your own.
I kind of like doing my own thing.
You enjoy that.
So
On a positive.
on this one,